Let us next see number 32. Here A in Fn is a Hermitian matrix and Ba to the power k equals the 0 matrix in Fn for some matrix B in Fn and positive integer k. Then we have to prove that Ba is also equal to 0. So we start the solution with the easiest value of k. Because k is a positive integer, k can be 1. And when k is 1, the hypothesis itself reduces to the conclusion. So then we directly have what we want. There is nothing else to do. Next we consider the case where k is at least 2. And now you look at this matrix. Ba to the power k minus 2 times A adjoint. This inequality takes care of the non-negativity of the exponent k minus 2. We do not want this exponent to be negative because we do not know whether A is invertible or not. Now what about this matrix? Because it's given that A is Hermitian, so A adjoint is equal to A. And then you can see that you will have A square here, which will get multiplied with this power of A and will become A to the power k. And by the given condition, the hypothesis, this is equal to 0. So that means this matrix is equal to 0. And you can interpret this matrix as the product of this matrix and A adjoint. That is equal to 0. So now you go and see what exercise 31 tells you. It tells you that when some matrix times A adjoint is 0, then that matrix itself has to be 0. So by that result, by exercise 31, this thing Ba to the power k minus 2 times A has to be 0, which however is Ba to the power k minus 1, because you can multiply these two. And that's how you have proved that Ba to the power k minus 1 is 0 using the hypothesis that Ba to the power k is 0. So the exponent has been reduced by 1. Now if this k minus 1 is equal to 1, that happens if our original k is 2, then this is where you stop, because then this is just this. Otherwise you repeat the process, this time with this condition, that Ba to the power k minus 1 is equal to 0. So when you repeat the process, you will get Ba to the power k minus 2 is equal to 0. And continuing like that, you will eventually get Ba equal to 0. So that is the solution. Next we have 36. I am leaving 34th one as a challenge to you. You see if you can come up with anything, and we can discuss about it later if you want. So in this 36th, it's the last one actually. If A commutes with this difference A adjoint minus A adjoint A, then we have to prove that A adjoint is equal to A adjoint A. That means this then has to be the 0 matrix. The solution may look very complicated at first, but let's see the steps carefully. So what we did first, we considered the given difference, that is this entire matrix, A adjoint minus A adjoint A. Instead of saying adjoint every time, I will say A star. Okay, A star minus A star A times its adjoint. Okay, and we are considering the trace of that product. Let's see what we get from this. So first of all, the first job to do is to take the star inside this difference. So that means this part will stay the same, and here we will have adjoint on A star first, A star adjoint minus, then we will have adjoint on A star A minus A star A adjoint. Okay, then in the next line also there is nothing to do here, not yet. And what happens here, you know that when you take the adjoint of a product that is equal to the product of the individual adjoints of the individual matrices, but in the other order. That means this is equal to A star star times A star, but A star star is equal to A, so that's why you see A here, A times A star. Similarly, this one will be A star, you see A star here, times A star star, which is A. Okay, and then the next natural thing to do in the next step is to do the multiplication. And in doing multiplication, this is how we went. We considered this as a single matrix, and then we multiplied this difference by this matrix. So originally you will get this matrix times A star, but it's given that this matrix commutes with A, so that A can be brought to this side. You see, originally it is this times A star, so A can now be brought to that side because of that commutation. So A comes here, the matrix sits in the middle, this one, followed by A star. What did we do here? Here we did ordinary multiplication. I mean, we did not do any twist or anything, just simply this times A star A. And then once more, of course, there is more multiplication to be done, and this time we just do it simply the way they appear. A star A star, A star A star, minus A star A star, A star A star, minus A star A star A star A star A, minus minus plus A star A star A star A star A. Okay, and then so the next natural step, of course, is this, after this, where trace gets distributed over the matrices in this combination. Why? Because trace is a linear transformation. We already know this property of trace. So trace of this minus trace of this minus trace of this plus trace of this. All right. And then what do we do? Then next we recall that property of trace which tells us that if A and B are two matrices, then trace of AB is equal to trace of BA. You can change the order of the product of two matrices inside trace. Not that AB is equal to BA, but their traces are equal. And we use that property here with this first product itself. And to do that, we interpret this as the product of two matrices. One of them is A star, and the other one is A star. So if you change the order, A star will come first, followed by this. See, A star, and then A star. Okay. And the next two terms we keep as they are. A star, A star. A star, A star, A. But then we did again another that type of change to this fourth one. Same thing. We treat this also as a product of two matrices. One of them is A star, and the other one is A. So after changing the order, A comes first, followed by A star, A star. Now what do you see here? Now you see that two terms have become identical except for their signs. A star, A star, A star, A star. This is minus, this is plus. So that means they are gone. And then in the next step we do again another that kind of change. Now to this. And treating this product as a product of two matrices. One of them is A star A and the other one is A star. So now after changing the order, A star will come first, A star, followed by A star A, A star A, and this one we are not changing, minus trace of A star A. So you see that these are also the same except for the signs, and that's how you get 0. And now you go and see the statement of exercise 29. I won't say exactly what the statement is. I want you to figure out how that exercise with this situation implies that our original matrix A star minus A star A hence has to be the 0 matrix, and that's why A star should be equal to A star A. So that's how we proved this. So that ends this section finally, minus the exercises that we did not solve. So you try them out and see what happens. After this we have the next section where we study determinants. So that we will start next week. So see you next week with determinants. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.